Holy shit.
Hi guys, in this video I'm going to talk to you about knockoffs, and I'm going to focus on the original paper. Knockoffs is a method developed by Rina Barber and Emmanuel Candes, these two fellows over here, and the original paper came from 2015. Barber did her postdoc at Candes, and I just thought it would be nice to mention that Candes did his PhD with David Donahoe, which is very famous for compressed sensing, and his name crops up a lot in statistics, at least in my courses. So he's a very interesting guy, at least for me. I would definitely check more of his stuff, and I probably will make more videos about material that came from him. But yeah, the original paper is by these two fellows, and Candes, my professor told me he's like the rock star of statistics right now. And so he's very, very famous and very, very strong in statistics as well. And I heard that also Rina Barber is a very good statistician. So what is knockoffs? Well, which domain are we in? Suppose you have linear regression. You have some response variable y, and you have some covariates that you want to test whether they are related to y or not. So you want to do inference, basically. Okay, and say you have a bunch of these covariants, and what it comes down to is basically you solve the linear regression, you get your betas estimators, and you try to test whether the betas are actually significant or not. So you have a lot of null hypotheses that the betas are actually zero. So you start with this null hypothesis that all the betas are zero, and for some betas, the betas are so different than zero that you say, no, it has to be that the betas here are actually significant. And it means that the x's, the features are actually significant, and they are affecting the y's. So in a way, it's a problem of multiple comparison and multiple testing, which I've talked about in previous videos. And what we want to do, we want to control for the FDR, for the false discovery rate. And in a previous video, I mentioned that one method to do this is using the Benjamini-Hochberg method. But what the knockoffs allows us to do is it allows us to do it, and it's better than the Benjamini-Hochberg. And it's better in two ways. First, it has much greater power than Benjamini-Hochberg. And second, it also allows us to do it in this linear regression case, because remember, the Benjamini-Hochberg has a condition that the hypotheses are independent. And in usual linear regression, the betas are not independent. There will be some covariance metrics. Yeah, the covariance will be sigma squared times xtx minus 1. Yeah, so unless xtx is equal to I, the identity matrix, unless this happens, the betas are dependent. And in this case, you can't really use the Benjamini-Hochberg. You can use the Benjamini-Equi-distant, which is, I mentioned very briefly, it's basically you add some terms, and it's a bit stricter and more, you will get less discoveries. But yeah, the knockoffs allows us to do it in this case, and it's better, and it will have greater power. So what's the main idea of the knockoffs? So knockoffs, as its name implies, creates knockoffs, creates cheap imitation of the original features, or the original x's. So for each x, j, we will denote by x tilde or x wiggle j, the knockoff version of it. Okay, and it has to be very similar to the original in certain things, but it also has to be a bit different. But what we know about it is that it doesn't have anything to do with y. Okay, so then we use some variable selection procedure for both x and x tilde. And what we get is that we basically compare the beta j with the beta j tilde, yeah, the xj with the xj tilde. And one thing to note is that if the signal, if the beta j tilde is bigger than the beta j, then this kind of raises a red flag, right? I mean, if the fake x has a stronger signal than the real x, then maybe both of them shouldn't be in the model, right? And so basically, the percentage of the knockoffs in our discoveries will give us an indication of the FDR. And in this graph, you can see it like this. Okay, so suppose that the black dots are our original features and the blue dots are our knockoff features. And we use some variable selection procedure, and we get for each feature some importance score. Yeah? And let's say we cut the score at 1, so everything below it we don't consider. The number of features here that basically passed the threshold, okay, this number over here gives us an indication of the FDR, and the FDR is kind of like this divided by this. It's kind of like, if we get more specific, this was one-dimensional. Yeah, we only had one dimension. On the other dimension, it was just the index. But instead of this, let's make it two-dimensional. Yeah, so in the x-axis, it's the important feature, it's the feature importance value given for the original feature. And in the y-axis, it's the feature important value that was given to the knockoff. So everything below the diagonal will basically means that the original feature got a stronger signal, got a stronger importance than the knockoff. And everything above the diagonal means that the knockoff got a stronger and better signal than the original. So what the knockoff method says is ignore for a second the red and the black. Yeah, the red and the black is the true thing, but we don't know the truth. Yeah, so if we ignore the truth for a second, then I counted here and say that the threshold is 1.5. So everything here we throw, and we are just left with these hypotheses, or with these betas. And I counted 9 points here and 18 points here. So what the knockoff method will tell you is that the FDR is controlled by 9 divided by 18, which is 0.5. And now if we actually put the colors back and count, well, there are actually 8 true discoveries here and 10 false discoveries here, the black dots. So it's almost 0.5, you see. And this is the knockoff method in essence. So how do you actually do it? Well, it's made out of 3 parts. Yeah, you have to construct the knockoffs. You need to somehow construct these knockoffs. Then you have to calculate the statistics for both original features and the knockoffs features. And then you have to choose the model according to your desired FDR. So let's go step by step and see how you do it. Okay, so how do you construct the knockoffs? Well, the first thing you do is you take your features and you normalize them. You divide them by their norm. And then you look at the gram metrics. The gram metrics basically represents distance between features, yeah, correlations between features. So what we want our knockoffs to have, we want our knockoffs to have certain properties. The main thing we want is that we want that x tilde transpose x tilde, it will be the same, will have the same correlation, the same gram matrix as our original xdx. And what it means that each feature with another feature will have the same correlation as every feature, as every original feature with the other feature, yeah? And another thing we want is that x transpose x tilde will be equal to this gray matrix, except in the diagonals, okay? So what we want is that we want that our knockoff feature will have the same correlation with any of the real features, except for the real feature that corresponds to the knockoff, okay? And if we denote, for example, this matrix of the real features and then the knockoffs together by x star, then x star transpose x star is basically this thing over here. Yeah, we will get this big sigma here, and in the off diagonal sigma minus diagonal s, sigma minus diagonal s. Now, the diagonal s, s is some vector, and it has the values there are non-negative. And what we want basically that xj transpose x tilde j will be equal to sigma jj minus sj, but sigma jj, since it's normalized, it's 1 minus sj. And we want to bring it as close to 0 as possible, yeah? So what we want, basically, we want that our feature, our knockoff feature, has the same correlation with all the other knockoff features as the original feature has with all the other original features. We want it to have the same correlation with the original features, except for the original feature that corresponds to that knockoff feature. And what we want, we want that the original feature and the knockoff feature of the same feature, yeah, the same j, we want them to be as orthogonal and as perpendicular to each other as possible. Okay, and the more orthogonal they are, the better the power of the knockoff method. Yeah, and this is basically what's written here. And there are two ways to do this. It basically becomes an optimization problem because we want these properties and we have this data. And so there are two ways that is suggested in the paper. One way is to say, okay, we want that the diagonal will be the same. Yeah, so we want that Sj is the same for all j. And in this case, it becomes a linear algebra problem and can be solved. There's a solution for it. And another thing we can do is we say, okay, we want to minimize the sum of the diagonal. Yeah, the sum of the diagonal of this matrix over here. And of course, it's subject to this thing over here and also this property over here. Okay, when what this means is the Loevner order. Yeah, it means that 2 sigma minus diagonal s. If we denote this by A, then this matrix A is positive semi-definite. Okay, I won't go too much into details in this video. Probably in a future video, I will cover this a bit more in depth, but it's doable. Yeah, you have the matrix and you have some optimization way to generate the knockoffs. And once you have the knockoffs, then you can calculate statistics for them. So the example they showed in the paper is the Lasso example. And what is the Lasso? You want to minimize this thing over here, which is basically the original thing that we always try to minimize in regression, at least in linear regression, and plus some regularization term, which is with the L1 norm. Yeah, and this thing promotes sparsity in the model. And the way we define the statistics is we take the largest lambda where the beta of that feature is different than 0. Okay, so how does it work? Well, in this graph over here, suppose that y is like the value of the betas and the x is 1 over lambda. Okay, so if lambda is infinity, 1 over lambda is 0. And in that case, all the features, all the betas will be 0. So our model will be just 0. Yeah, but if lambda is less than infinity, then we get some feature and his value starts to change. And if lambda is above, if 1 over lambda is above 0.2, which means lambda is less than 5. Yeah, so if lambda is less than 5, we get another feature over here, etc., etc. So if we take lambda to infinity, all our betas become 0. As we reduce the lambda, suddenly another beta comes into play. Yeah, and then we reduce it and another beta is different than 0. Yeah, so for each feature, we basically give it the lambda, and the lambda is actually a measure of how strong that feature is, because you need a very large lambda to get it out of the model. Yeah, or maybe you need just a small lambda to get it out of the model. And the more lambda you need means that the feature is more strong. So this is the statistic they chose. And also what they do is they do like this. Okay, so this is the statistic. They take the maximum between the original feature and the knockoff, and then they keep it if the original feature came before the knockoff, and they multiply it by -1. So they take the minus of that if the knockoff came before the feature. And so a large positive Wj is an indication of a genuine signal. Yeah, so it means that the genuine signal. And note that there are actually different procedures that you can do. You don't have to take the Lasso, and you don't have to take this function over here. There's just two conditions that you need to have. One is sufficiency, and the other is anti-symmetry. But both of them are fulfilled in this example. Yeah, if you are interested, just check the paper. Okay, so once we did this, now it's time to choose the model. So we can define a threshold, and the threshold will be the minimum such that the number of above diagonal divided by the number of below diagonal is below the FDR that we want to control. Yeah, it's below the Q. Okay, and basically, yeah, we start here. Yeah, and then we take the point and we take it down, 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 and we try to get it as small as possible. Yeah, so that the this divided by this is less than the FDR. In this case, it's 0.5, yeah, so it's not very good, but maybe if we take it more down, it's better. Maybe in this example, we have to take it even more up, yeah. But this is basically what it does, yeah. And this controls almost for the FDR, yeah. This controls for what they call the modified FDR. But this modified FDR works really good, except for a very pathological example where the correlation between the features is extremely high. But if you want to really just control for the knockoffs, then instead of this, just add 1 in the numerator, and then they call this knockoffs plus, and then this one controls the FDR completely. Okay, and once you get this threshold, you just choose all the features that their W, the statistic that we calculated for, are above that threshold. Okay, and again, it turns out this method controls for the FDR as well. In a subsequent paper, they proved it also controls for the directional FDR, which is a bit better, but I won't go into this either. Okay, so what is the intuition behind the knockoffs? You already got some intuition from the graphs, but the main idea is that for the null betas, for the null features, we expect that the signs of W will be IIDs, so independent and identically distributed. What it means is that we expect that the number of J's such that beta J is equal to 0, so we're in the null, yeah, the feature is not really important, yet the WJ is above the threshold, is equal in distribution to the number of J, again, that the beta J is equal to 0, but that the WJ is less or equal to minus T. So the number of features that are null and that are knockoffs gave them a very strong value. Yeah, we gave them a minus value in the end, but before we gave them the minus, they had a very strong value. This is exactly equal to the number of features that are null, and our knockoff value gave them a strong feature. Yeah, but this is only for the null. It's not for the non-null. It's not for the real features that affect the Y's. Okay, so if you believe this, then this quantity over here, which is basically the false discovery proportion, yeah, because we take all the J's that have this, so the number of times we were wrong divided by all the discoveries we made is approximately this over here. We just replace this, the numerator, with this because we said they have the same distribution. Okay, so this is less than equal than this because there are two conditions here, yeah, that the beta J's are 0 and that the WJ is less than equal to minus T, but we don't know that which of our W's have a beta J is equal to 0, but it doesn't matter. It's a subgroup, so this quantity is bigger than this. And this is exactly what we control for, yeah? This is the knockoff method. Yeah, this is what the knockoff method will say is the FDR. So we control for this quantity that we want to control with this. Okay, and we can even look a bit further down into it. So remember, what are the coefficients estimates for the betas? It's just this expression over here. And let's ignore this part. Yeah, it's just a matrix A, which is the same for both the knockoffs and not the knockoffs. Let's look only at this. Okay, so what we say is we say that for a null feature, let's say xj is null, then xj transpose y is equal in distribution to xj tilde transpose y. Okay, so remember that xj transpose xj is equal to xj tilde transpose xj is equal to sigma jj, which is also should be equal to 1. Yeah, and remember that xj transpose xk is equal to x tilde j transpose xk is equal to sigma jk. Yeah, the correlation between two original features should be preserved between the knockoff feature and that other feature. Yeah, the correlation should be preserved. And the only thing different is this thing over here. Yeah, xj transpose xj tilde is equal to sigma jj minus the sj. Okay, and let's suppose that our real model is, for example, 3x1 plus epsilon. Yeah, so this means that y distributes normal with 3x1 and sigma squared times the identity matrix. So if we now take x2, which is a null feature, and we look at x2 transpose y, well, we will get this thing over here. okay? And if we look at x tilde to transpose, so the knockoff, we'll get this thing over here. But we just said that this has to be equal to this. This is how we build it. Yeah, we build it that the correlation of two features is preserved when we move to the other feature. Yeah, and this also has to be equal to this, because we just said that x2 transpose x2 is actually has to be 1, and it has to be the same here as well. So we get that both of them have the same distribution. Yeah, and notice this wouldn't be the case if we used x1, yeah, because x1 transpose x1 is one thing, but x1 transpose tilde x1, it's this thing over here. It's not the same. So it won't be the same here, and it also won't be the same here. So it's only true for the null. And this is, I hope, gives you even more intuition into the knockoff method. Okay, so how is this compared to the Benjamini-Hochberg method? So as I mentioned, first remember that there is an assumption of independence, but this doesn't happen in linear regression unless x equal to I. So you can't even use Benjamini-Hochberg in linear regression, but you can use the small correction, which is the Benjamini-Hochberg, which is this thing over here. I mentioned this in another video. Okay, but still, how do we compare it? So the paper did some tests, and you can see here that the FDR is kept all the time. Yeah, for all the methods, both the knockoffs and Benjamini-Hochberg, the FDR, they set the FDR at 20%. You can see the FDR, the actual FDR is much below 20%. But look at the power. Yeah, the Benjamini-Hochberg power gets 50%, but it's not even guaranteed to control for the FDR. And 20% if you use the Benjamini-Hochberg. Okay, and there's another method that it goes down to even 2.3%. All the while, the knockoff method gets you to 60 or 67%. Yeah, so if we use the original knockoff, which doesn't control exactly the FDR, it controls the modified FDR, you get almost 67.5% power, which is very strong. But even if you just use the knockoff plus that is guaranteed to control the FDR, you still get 61.54% power, which is very, very good. It's much better than Benjamini-Hochberg. And here you can see different things that they measured. For example, if you make more signals, yeah, so let's say the X's you have, I don't know, 3,000 X's or 300 X's, but at first you only give 50 that really have a signal, and you change the levels. Yeah, so you can see that the FDR is controlled better for the knockoffs plus, and at least from this thing onward for the knockoffs, better than the Benjamini-Hochberg. But the power of the knockoff and the knockoff plus is always bigger than the Benjamini-Hochberg. Here they change the amplitude, yeah, as you make the amplitude better. So the signal, you can have the, for example, if you choose 50, yeah, and you make 50 out of the entire X's to really have a signal, and then you change the level of signal, you make it bigger. Okay, at first it's 2.8, and you can make it bigger till 4.2. You can see in that the FDR is still preserved, but you can see that the power goes up, of course. And again, the knockoff and knockoff plus has better power than the Benjamini-Hochberg method. And also for correlation, you can see that except for the very, very strong correlation of 0.9, then the FDR is controlled both for the knockoffs and the knockoff plus, actually better than the Benjamini-Hochberg. And the power is still always stronger for the knockoff and the knockoff plus. So this was the method. Some limitations that this method has is, first, it requires low dimensionality. And specifically, it requires that n is bigger than 2p. Yeah, remember that you take your p and then you multiply it. So the number of columns will be 2p, and you want that the number of rows will be bigger than this, or at least bigger, equal, maybe. Yeah. Yeah. Okay. There are extensions for this case where n is bigger than p, but smaller than 2p. They do it in the original paper. I won't go into detail. In another paper, they also offered using sure independence screening when p is much greater than n or just greater than n, and you reduce the p to some subset that is less than n divided by 2. And once you have this, then you can use the knockoffs. Okay, so this is one problem. This is one limitation of the knockoffs. The second limitation is that it is restricted to linear models. And the statistics must have this sufficiency property that I didn't go into depth. But there is an extension in later papers to what they call model X, which basically you don't assume so much about the structure that connects Y and the X, but there is a trade-off. You don't assume so much about this, but you have to assume more about the connection between the X's themselves, about the structure between X's themselves. Okay, so this will be something that I will cover in a future video. Now I want to show you this a bit in code. Okay, so this is an example taken from their website of the knockoffs, but which I had just adjusted a bit. So yeah, let's suppose we want 1,000 observation. We want that we have 300 variables, and we want only 30 of them to actually have a signal, to actually have non-zero signal. And the amplitude that will give these non-zero signal is 4.5. Okay, and now we create this data, and we create it with autoregression correlation. Yeah, so the features will be slightly correlated. The correlation for each feature with the nearest feature is 0.25, and from every subsequent feature is 0.25 squared and 0.25 cubed, etc., etc. So this is, they create this this covariance matrix, which is autoregression, with this autoregression correlation, and then they create X's. They draw samples from with mean 0 and this covariance matrix. And this is just a way to do this. You could have also just used a package that draws from multivariate normal and supply the sigma. Here they just basically use a Cholesky decomposition on the sigma. So it's kind of like half sigma to the power of half. And then by multiplying this, the distribution is 0 and sigma. Okay, and now they choose 30 out of the 300 randomly, and they give it the amplitude, which is 4.5 divided by square root of 1,000. Okay, and then they create basically the Y's, which is just this model. It's X times the beta that they use plus some noise, and this is the Y's. Now for the fixed X knockoffs, which is what I showed you in this lecture, it's called fixx. We use the library called knockoffs, and the only thing we need to do is called knockoff.filter and give it the X, the Y, say create fixed, because this is the model, the fixed X model. And then we have to say which statistic we want, and there is a statistic called stat.glm net lambdas max, which is exactly this lasso thing that I told you about. And you can also specify the FDR. The default is 0.1, which I will leave. Okay, and you can see it takes some time. It will take a few seconds. Okay, I'll be honest with you guys. I just ran this a few times, and in these few times, it came out that the Benjamini-Hochberg method actually was not worse than the knockoff method, and even better sometimes. But before that, I ran it, and it came out that the Benjamini-Hochberg was much worse. And now I think I came to another example where the Benjamini-Hochberg was much worse. So these are our results that came out from the Knockoff-filter. We can see we have 25. We can see that 24 out of them are actually true. So the power and the power is 0.8, so 80%, and the FDR is 0.04. Okay, and now if we do the Benjamini-Hochberg, we get that 27 are rejected null hypothesis. So 27 X's are important. The power is 0.9, so even stronger power. Yeah, remember that before we had 0.8, but the FDR is 0.341. So much, much worse than 0.1 that we wanted. And this is because we use the Benjamini-Hochberg. So let's use the Benjamini-Equi-distant now and see if there's any difference. Okay, so we see we went down to only 18 discoveries, and the power went down to 0.6. Remember, in the knockoffs, we had 0.8. And now the FDR is indeed below 0.1 and 0.05. Okay, so You can see that the Knockoffs method is usually better than the Benjamini-Hochberg. I do have to say that in certain times that I ran this now, the Benjamini-Hochberg did came out better, but I guess it's just a coincidence or random chance. But overall, the Knockoffs method should be better. So this is all I wanted to show you in this video, and hope you enjoyed, and see you in the next one.